Welcome to a new video on my channel. This is Python Basics for Machine Learning. In today's episode we are gonna have a look at NumPy. Just as a heads up, this series is targeted for beginners, but there may be some tricks and tips that also advanced users can profit from. So let's start. But wait, what is actually NumPy? When we have a look at the official GitHub page, it is written that NumPy is the fundamental package for scientific computing with Python. It provides a powerful n-dimensional array object. By the way, you can find the link to the GitHub repo down below in the descriptions. Well, why do we need NumPy's n-dimensional array object when we have already lists in Python? Well, NumPy functions are implemented in C, that's why. Every element in a NumPy array has the same type. So imagine NumPy arrays are like densely muscle-packed lists on steroids. Plus, the elements in a NumPy array are stored as a continuous block in memory, allowing to take advantage of a principle of locality of reference, unlike lists. Very interesting principle. Look it up if you have the time to. So, without further rambling, let's explore the realm of NumPy. When we talk about NumPy arrays, we often refer to different n-dimensional NumPy arrays as being vectors if they are one-dimensional, matrices when they are two-dimensional, and higher order matrices or tensors when talking about three or higher dimensional NumPy arrays. Because that is the picture that we have in mind when we use NumPy arrays in order to do linear algebraic computations. And here we are already in the heart of NumPy. NumPy is just a fantastic library when we want to express linear algebraic equations and computations in code, and want to compute them very effectively. But the reality will more look like this, where this matrix is actually represented like this sequence of numbers that are grouped together. Each group would correspond to a row in our matrix, but there are not really any columns. But if we would take each group and stack them vertically, we would end up with our matrix. That's our mental model that we work with when we use NumPy. Also, it helps if we clarify a few terms before we dive into the code. When we say that an array is three-dimensional, then of course we refer to 3 as being the number of dimensions, very simple. But there's also the notion of axes in NumPy, which can be hard to understand for beginners. In NumPy, the term axis refers to a specific dimension of a NumPy array. The axis parameter is used in various NumPy functions to specify along which dimension operation should occur. Also good to know, axis objects are zero indexed, so we start with 0. Then axis 1 would be along the columns, axis 2 along the depth of this matrix. NumPy has also something that is called shape. The shape specifies how many elements are stored in each dimension. In the first dimension we got 3 rows, in the second dimension we have 3 columns, and in the third dimension we have a depth of 2. The length of the shape object is equal to the number of dimensions. When we multiply each number in the shapes with each other, we get the total number of elements in our NumPy array. Convenient, isn't it? Now we have talked a little bit about the terms that we encounter in the world of NumPy. Let's see how this all translates into code. So that's the code we are dealing with today. Very simple, we just have a main function. We have NumPy imported already, and I've already set up some toy scalar values and toy lists, and that is a list of lists, and we'll see what we can do with them. First, let's talk about lists for a second. How do we get an element from a list? Well, we know that elements in a list can be accessed via indices. So how do we get the element, the first element of X, and the second row first column element from Z? I invite you to follow along and to code it up before I show you the solution, so pause the video and do it yourself. So here's the solution. So it is very simple. We just use the square brackets and put in an index to the element that we want. If we have lists of lists, then we have to select the most outer list inside of our list and go from outwards to inwards until we have reached the element that we wanted. If we run our script, we should get out 0 and 1. So let's do that. And as we can see, we get 0 and 1. And by the way, this here doesn't work, for example, in order to simplify the square bracket notation. So if we do that, you can see this doesn't work. So, but how do we start with NumPy? Well, before you can actually execute any code that contains NumPy code, you have to install NumPy to your virtual environment, Conda environment, whatever you are using. NumPy is available via PyPy. I will link it in the description down below, so do the installation first. By the way, if you want to see a video where I show you how to set up your own virtual environment and install Python libraries in it, just write it down in the comments and I will make a video if some people are interested in it. So, how do we convert these lists that we have into NumPy arrays? Well, it's actually very simple. This is how you do it. There's a function which is called array, which is part of the NumPy library, and this function will convert our lists into NumPy arrays. It's very important that the elements inside of our lists are compatible with each other in regard to the data type. So we have seen how we retrieve the first element of X and also elements inside of a matrix or lists of lists. So how can we do the same with NumPy? Well, this is how you do it. You get the second element of X, for example, by doing X square brackets 1, so it's the same notation as with lists. And when we have a multi-dimensional NumPy array, we just have to use 2 indices in order to retrieve a single element. And what we also can do is we can also use this notation which I showed you before. That didn't work for lists, but for NumPy arrays it does. And what is also very helpful, if we want to take the first row, we can also use the column character. So when we put the column character here, what this will mean is that we will want the first row of that and all the elements inside of it. And when we want the second column of that, we can also do it with the column character, comma 1. Actually, in this case, to get the first row of that, we actually don't need to use the column, right? You could also do it like this, for example. And as we can see, indeed, we get the results that we would expect. Sometimes we wish to create NumPy arrays which have all the elements already pre-filled with some value. For example, their value could be 0, it could be 1, it could be any value that we want. And of course, NumPy provides functions for us to do that. For example, these ones here. For example, np0s, so zeros is a function which expects a shape. And in this case, we are giving it as an argument the shape of 2, 2, which would mean that we will get a matrix filled with zeros, which is 2 by 2. We can also see that when we execute our code, we can see here that our matrix has only zeros. What we can also do is we can use the function once, and once will initialize all the elements inside of our NumPy array to 1. In this case, we have specified the shape to be of 3, 1. So we want to have 3 rows and 1 column, and that's what we get here. And what we also can do is we can multiply our NumPy array with a scalar value, and that will leave us with a NumPy array that is not filled with ones, like it would be when we would leave out the multiplication with alpha. But since alpha is 0.5, as we specified here above, all the elements inside of our matrix will be multiplied by 0.5, and 1 times 0.5 is 0.5. And this is what we got here. And if we want to have values that are randomly assigned, NumPy can help us out here as well. So for example, with the function random.randn, we can specify the number of dimensions that we want. For example, in this case, we say we want 3 elements. So we don't specify the number of dimensions by the number of elements in the first dimension. And if we want to have to add more dimensions, we can do like this. We can say comma 2. That would mean we would like to have a 2-dimensional NumPy array where the first dimension will have 3 rows and the second dimension 2 columns. And here, as we can see, all randomly initialized, randn initialize them from or is sampling the values from a standard normal distribution. NumPy has a lot of utility functions like that. What's also very helpful is that we can specify explicitly a D type, so a data type for our NumPy array. For example, here we have a NumPy array filled with strings, and we specify the d type to be equal to string. And when we print our NumPy array and the d type, we will get the following answer. Of course, we will get our NumPy array back, and we will get something which is smaller u5. Well, you might think, well, this is not what we specified, right? Because we specified string. But what is a string? A string is a sequence of Unicode characters. Our largest string has 5 Unicode characters in it, right? NumPy. And this is why we get the u5, because the 5 stands for the number of characters. And the smaller sign or bigger sign, which can also occur, is standing for the endianness. So there's something which is called little and big endian. If you don't know what this is, look it up. It's also a very interesting topic. It has to do with CPU architectures, but this shouldn't bother us here. Important thing to know is that U stands for Unicode and 5 stands for the number of characters in this case. Of course, we can also do some computations with NumPy arrays. For example, we can multiply our NumPy array x with a scalar value. We already have seen that. Or what we also can do is we can add a NumPy array with another NumPy array. Or what we also can do is we can do a scalar value multiplied with a NumPy array plus another scalar value times another NumPy array. This is also, of course, also possible. If we want to compute the scalar product between two NumPy arrays, this is also very easy. We just have to use the dot function. So each NumPy array has access to this dot function, and there we specify the second NumPy array over which the scalar product should be computed. So if we print this out, we can see from before the scalar computations, they all work, and also the scalar product is correct, it's 8. Right, because the scalar product between x and y would be 0 times 1 plus 1 times 2 plus 2 times 3, this is equal to 8. Of course, when we are dealing with linear algebra, the transpose operator shouldn't be left out. And of course, NumPy has also the transpose operator as an attribute on our NumPy array. And when we execute our little code here, what we get is that the transpose of x is 0, 1, 2. So we don't see a difference. Of course, not because it's a one-dimensional NumPy array. And NumPy doesn't know the notion between row and column vectors. So of course, we don't see a difference. The shape is also the same. But if we reshape our objects, this is another utility function from NumPy, we can take our array, which is x in this case, and reshape it to another compatible dimension. In this case, we take 3, 1 as the shape. And when we do the transpose of that, we also don't see a difference, but we see a difference in the shape. The shape is now 1, 3 instead of 3, 1. Since we are already talking about shapes, we can of course also have a look at our shapes. So when we take any NumPy array and access the attribute shape, we will get back the shape. And we can also ask the shape object, okay, what's the first shape dimension of that? What's the second shape dimension of that? And we can also say, what is the total dimension of that? So in this case, the dimension of that is 2 because it's a 2-dimensional array, right? A matrix, essentially. And the first shape is 3 and the second shape is 3 because we have 3 rows and 3 columns, right? And the shape of that in total is here specified. It's 3, 3, as we would expect. So this is really convenient. Keep this in the back of your mind. And of course, we can also do more complicated computations. For example, the matrix vector product. We can take any matrix and we can multiply it with the dot product with any NumPy array. Note though that the shapes have to be compatible. Like these are essentially the same rules as in linear algebra. NumPy arrays have a few more, let's say, special cases, but this shouldn't bother us here. And here I have written out how the computation would work, right? So we would take the row of a matrix, multiply it out with the column of our vector. Well, we have only one. And then we do the scalar product between them, right? 0 times 0 plus 1 times 1 plus 0 times 2. And then we take the second row times the column, the third row times the vector, right? You probably know this from math classes. And as we would expect, this also works. It's 1 to 1. But there's one edge case which I want to mention. And this is, for example, if we, for example, take our array, so x had the shape of 3, nothing. But when you would reshape it to having an explicit 1 at the end, then it can mess up with your computations. For example, when we take the matrix vector product between Z and A, where Z is our 3 by 3 matrix and A is our vector, well, here you see A is derived from X but reshaped, right? And if we compare, or if we print out the shape of A and the shape of Z, what we will see is that the shape of A is 3, 1, because that's what we specified over here, right? And Z is 3 by 3. And when we have a look, so a 3 by 3 times a 3 by 1 multiplication will leave us with a 3, 1 shape, right? Because we are doing a multiplication over, because we are taking each row of a matrix and multiply it out with each component in the vector, right? So we are eliminating these two. So we eliminate essentially an axis and are left with 3, 1. And when we wouldn't specify this explicit one, we would get 3, nothing, and this is what we would actually expect. Of course, we can also do the vector matrix product. This is also possible. So for example, we can do the product between Z and X and Z. So we take X dot Z, and when we compare the shapes again, this is what we get, right? 3, nothing times 3, 3 is equal to 3, nothing. And another function which is pretty convenient when you work with NumPy arrays is that you are able to stack multiple NumPy arrays. For example, you can take the NumPy array X and Y, and you can do a V-stack, a vertical stack, which means row-wise. So if we run our script again, okay, we have to save it. So what you can see is that we take our X NumPy array, which was 0, 1, 2, and our Y NumPy array 1, 2, 3, and we stack them row-wise. So we would have a larger NumPy array where the first row inside of this NumPy array would correspond to X and the second to Y. What we also can do, we can of course take the transpose of that, and in that way we stack them column-wise instead of row-wise. And since we talked a lot about dimensions, axes, shapes and so on, I should give you a slight introduction into working with axes. So for example, if we have an array like this, G is a NumPy array, which is a 3 times 3 array, and NumPy offers a lot of functions which are very convenient. For example, the sum function is one such an example, where it inputs an array, in this case G, and it wants to know an axis that you have to specify. And for example, if we take the axis equal to 1, we will sum up all the elements along the column axis. That means row-wise. So what we would calculate is, so the first row sum would be 0 plus 1 minus 2. This would be equal to minus 1. Then we would take 1 minus 1 plus 3 is 3. 2 plus 3 plus 4 is equal to 9. So we would to expect that this here gives us the result minus 1, 3 and 9 as a NumPy array. When we execute that, we can see that this is true. And when we specify the 0 axis, so we go along the row axis, we would make the column-wise summation. So in this case, we would sum 0 plus 1 plus 2, it would be equal to 3. The second column sum would be equal to 3, and the third one equal to 5. So we would get 3, 3, 5. Or if we wouldn't specify any axis, so equal to none, so this is also the default, then it would sum over all the elements in our NumPy array, and this would be equal to 11. So it's really important to get a hang of these axes, because it's just vital for getting the right results in the end. And of course, it goes without saying that we also can do something like sine and cosine. This is also pretty simple. Don't be confused here, this should be actually equal to 0, and this also, because the sine of minus pi and pi is equal to 0. Of course, in computer science we get when we're working with a computer which is only able to calculate or do computations with a certain precision, we will get rounding errors like this. And of course in machine learning is all about statistics. Also the most important functions regarding statistics are not missing. Like doing a computation over the mean. So A is a NumPy array with the components 0, 1 and 2. And the mean of that would be 0 plus 1 plus 2 divided by 3 because we have 3 elements would be equal to 1. We can also, of course, calculate the sample variance of A. Why are we calculating the sample variance? Well, because it's important here because of the degree of freedoms which we have to specify in our variance function. So npvar is the variance function and it expects an array and the degree of freedoms. In this case, we want to calculate the sample variance since most of the time when we have data, we don't have the whole population of the data, but just a sample from that. So we have to calculate the sample variance. And the difference in the formula, so if you know the variance formula for the populations, the difference to the sample variance is this -1. And this is actually minus the degree of freedoms that we specify here. But the default is equal to 0, so you have to be careful. So by default, you would calculate the population variance. And of course, we can also calculate the standard deviation. Of course, we could take the square root of this in order to get it. But in this case, NumPy has also a function for us, also with the degrees of freedoms that we have to specify here. And when we run our scripts, we can verify that the computations I wrote down here as comments are correct. So it's the mean is 1, so that's what we got here. The variance of 1 got here, and the standard deviation, of course, also is equal to 1. And of course, VL norms are also not missing. So in machine learning, there's something called lasso and ridge regression. I made a video about lasso regression. I will link it in the info card here above if you're interested in it. And there we are using the L1 norm, for example, as an additive term in our objective function. So during your journey of machine learning, you will probably encounter those. So it's also important to know how to calculate them. And luckily enough, also NumPy is covering our back here. np.linarc.norm is what we want here. And the L1 norm, I have explicitly written it out here. If you don't know about it much, don't worry for now, but keep in the back of your mind that NumPy has this function already in place. And what it expects a NumPy array and the order, in this case 1, because we are computing the L1 norm. So, and the order is important because the exponent here and here will differ, because that is 1 over the order actually, and this is to the power of the order, right? And we can see that here, for example, the L2 norm is with the order 2, that's why it's called L1 and L2. And as you can see, the difference between these equations and this equation is that here we have the power to the 2, and here we have power to the 1 over 2, which is the square root of this whole thing. And we can see that the result should be equal to 3 and approximately equal to 2.236. And when we run our script, we can see indeed that is correct. So this is it for this episode. I hope this video was insightful. If yes, please like and subscribe. And if you got any other packages which you are very interested in and which are relevant to machine learning, post them down below in the comments. And when enough people are interested in that, I will definitely make a video about that. And showcasing the most important features or features that they offer that you will most likely encounter in machine learning. Until then, I can just recommend install NumPy, play around with it, read the documentation because the documentation is very huge. NumPy is a very large library offering tons of functions, tons of utilities. Just play around with it, just see what you can do with that, find the special cases, the edge cases where it deviates from the math knowledge that you know. And this will be a very good starting point in your machine learning journey if you understand how to work with NumPy, because most likely you will use it a lot throughout your machine learning journey. So I hope I got you well, and I see you in the next video.